we will take the second topic, the deflections in statically determinate trusses using strain energy method or unit load method. Both mean the same. Okay. Now let us see what is strain energy. Strain energy. This strain energy means similar to your potential energy, kinetic energy, we have another form of energy called strain energy. If you have a block of weight W, it is at a greater height, say, we say that it has some potential energy by virtue of its height. When you drop from there, it converts into kinetic energy. So that is about the block by virtue of the height. If it has some velocity, kinetic energy we call it. Supposing that if you strain a body, straining a body means pulling, pushing or shearing. Whatever way you strain the body, if you are able to store energy, then that is called strain energy. Strain energy means energy stored due to straining of a member. That straining can be pull, push, bend or twist. All four forms of energy expressions also in strength of materials we have studied. Now we will see the extension of that, how we have to find the deflections. Okay. Strain energy means energy stored due to straining of a body. Stored due to straining of a body. Due to tension, compression, bending, twisting, all forms of strain energy you have studied. We will discuss now only axially loaded members. Strain energy stored due to axial force, can be compression or tension, only that we will see. In bending, strain energy stored due to bending, we will study in the deflections of the frames. That also we will discuss. Their frame energy, their bending energy, we will take it at that point. Now, this is what you have studied. Strain energy stored due to gradually applied loading. Gradually applied loading is given by U is equal to area of load versus deflection curve. This is area of load versus deflection curve means how much you have applied the load, how much it has deflected, without worrying about the deformation in the member. Okay. So area of load versus deflection curve. This is the external applied load, external deflection. That means potential energy, we will get it from this. Potential energy lost or gained must be equal to strain energy stored in the member, like that. So assume that you have a gradual, you have a member like this, say. Length of the member is L, cross sectional area is A. You are applying some load W, and when gradually applied load is there, we know the deformation also, WL by AE. That means the applied load W, which is applied gradually 0 to W, that weight W comes down by an amount of WL by AE, which is also equal to the elongation in the member. By the same amount, W also will come down. External load, and how much load, how much of deflection that load undergone. Okay, WL by AE. Delta is equal to WL by AE. If you take this diagram, load versus deflection curve, what is that area is like this. This is delta. This is W. This W is applied load. This is deflection. This delta stands for deflection. Deflection of W means how much W has come down or whatever it is. Initially applied load is 0. Gradually applied load means that initially zero load will be there and you want to apply 100 kilonewtons say. Time taken will be very large, maybe half an hour time like that. First zero load, 0 kilonewton, then 1, 2, 3, 4, 5 like that, 100 kilonewton if you want. Sufficiently large time will be there to apply that 100 kilonewton load. Such loads are called gradually applied loads. So when the applied load is 0, deflection is also 0. As you are increasing the load, then deformation in the member increases, so the load also will come down. How much load is coming down is this one. How much you are applying load is here. So load versus deflection curve, as the load increases, how much it goes down is like this. So this is area of load versus deflection curve. This is W, and from here to here, how much it will go down is how much that load W, initially 0, finally it reaches W. By the time your applied load reaches the magnitude of W, that W might have come down by an amount of delta. That from strength of materials you have learned how much it will go down is WL by AE. So potential energy lost we will get from this diagram. Initially there was no load. As you are applying the load, it is coming down means what? Potential energy is lost. So this is the curve. This we call it as U, let us say. This is potential energy. Lost by weight W. Whatever potential energy lost by the weight, who will store it? Energy can neither be destroyed nor created, type stories you have studied. So potential energy is lost. Whatever potential energy lost by the weight will be stored in the form of strain energy in the member. So this is now equal to strain energy stored in the member means you will write now like this. Strain energy stored in the member means you have to take here it as resistance. Resistance versus deformation. Initially 0 deformation, 0 resistance. As the resistance increases, deformation also increases. Means as the deformation increases, resistance also increases. Okay. This resistance, how much is, we know that formula also. This is the deformation delta. For this deformation delta, what is the resistance means you have studied from the strength of materials. Delta is equal to, this is from SOM. Delta is equal to WL by AE, where W is equal to internal resistance. This is what you have studied, internal resistance into length by AE. Now if you want to find the resistance, as long as the bar is not broken, resistance is equal to applied load only. So resistance is equal to AE by L into delta. So now resistance here it is AE by L into delta. So as the deformation is increasing, resistance also will increase. So this ordinate is AE by L into delta. This is the internal or strain energy stored in the member. Now this area, this potential energy lost, strain energy stored. Always they must be equal. Now you see, if you take the area of the load versus deflection curve, area of load versus deflection curve, half base is delta, height is W. Half the deflection formula we know WL by AE into W. So you will get W square L by 2 AE. This is in terms of external applied load. Now if you want to write in terms of internal stress terms, if you want to write, I can write it as W square L by 2AE into area divided by area we can write. This we simplify it, W square by A square into A into L by 2E. W square by A square we know F square by 2E into volume. This is in terms of internal W square by A square when you are writing in terms of internal resistance per unit area. So this is in terms of internal resistance, F square by 2E into volume, where F stands for resistance by area. Volume means volume of the member, area into L. So this is the second expression for the strain energy stored. Strain energy stored, potential energy lost is same. Third way of writing is W square, area of load versus deflection curve. From the strain energy curve also you can write half into delta into resistance, AE by L into delta. This way also we can write half base into height. So you will get delta square by 2L into AE. Later stages you will learn that this expression, that strain energy expression, we use it in the stiffness method of analysis. In terms of applied loads when you are taking, you will use this expression for the flexibility method of analysis. Okay. So in terms of potential energy, we will write there in the flexibility matrix methods of analysis, we use that form of energy. Energy in the form of deformations we use in the stiffness method of analysis. Okay. So this is how there are three expressions for the strain energy. Generally, if you write in terms of W square L by 2 AE say, that we will write the complementary energy. This is strain energy, that is complementary energy we take it. That means complementary energy expressions we use for the flexibility method of analysis. Strain energy expression we use it in the stiffness method of analysis. Okay. So there are three expressions for the energy in terms of applied load, in terms of internal stress, in terms of deformations. Okay. Now, you can also apply, this is for the gradually applied loading. We can also apply the load suddenly. That means instead of applying gradually 0 onwards it is increasing, entire load W can be applied at once. That means like this 0 it will not start, it starts from W itself. If the load starts from W itself instead of 0, then the area of load versus deflection curve will change, but area of strain energy curve, that means resistance versus deformation, will not change. Whether you apply load gradually or suddenly or with impact, the deformation starts from 0 only, always, for all cases. So this curve will not change, but this curve will change depending on how you apply the load. Now let us see the third concept, strain energy stored due to suddenly applied loading. Third point is strain energy stored due to suddenly applied loading is given by Again, U is equal to area of load versus deflection curve, or area of resistance versus deformation curve. Deflection is the word we use it when the load, how much it has come down. Deformation means how much member has deformed. Sometimes the deflection and deformation may be equal, sometimes they may not be equal. In the impact loading cases, we will see that deflection and deformation will be totally different. Okay? So, now you see this diagram, load we are applying suddenly. Delta will not be WL by AE, some other value will be there. This curve also will not be like this. This is different, but this will be same. Since the load is applied suddenly, this load versus deflection curve will go now something like this. Load versus deflection. Now you have started, beginning itself load W is there and it will go like this. If it goes down by delta, let us say, this delta now, this is the ordinate is W, this is delta. Now if you want to see how much that delta, we will find it like this. In strength of materials you have studied, depending on how you apply the load, deformation characteristics are totally different. If you apply the load suddenly, how much should be the deformation so that areas will be equal? So that we will find from this one. Potential energy lost by weight W must be equal to strain energy stored in the member. Potential energy lost how much? W into delta. Strain energy stored half base into height. AE by L into delta. Okay, this is potential energy. This is strain energy. Okay, whatever may be the type of loading, potential energy loss must be equal to strain energy stored. So delta delta cancels out. How much you will get? Delta here is 2 WL by AE. If deformation is 2 WL by AE, only then rectangle area, triangle area will be equal. That means when you apply the load suddenly, the deformation is 2 times WL by AE. Like this. So this is 2 WL by AE. Now you can calculate area of the load versus deflection curve means this delta just now you calculated, it is 2 WL by AE. It has to be 2 WL by AE, only then this and this areas are equal. So rectangle area, triangular area will be equal only when delta is 2 WL by AE. So now if you take this U value, U is equal to W into delta is equal to W into delta is 2 WL by AE. So you will get 2 W square L by AE. This is expression 1 for suddenly applied load. If you write in terms of strain, internal stresses, this we can write it as 2 W square L by AE into 2A by 2A we can write. So you will get it as 4 W square by A square into AL by 2E. That means F you take it as 4w by a square means what? 2w by a whole square. F square by 2e into volume, where F means 2w by a whole square, where F is equal to, we call it as instantaneous stress, is nothing but 2w by a. Then delta, in this case we get it as instantaneous elongation. Two WL by AE. So this is in terms of the stresses. In terms of applied load, in terms of internal resistance. Now, instantaneous stress means at what instant stress we are calculating? We are calculating at the instant of not applying the load, at the instant of reversing its direction. At the instant of applying the load W, delta is 0 only. Deformation is 0. You have to wait for some time. Then it goes down, reverses back. Why should it reverse back? See here. If you see this diagram, if you take instead of 2WL by AE, take only WL by AE amount like this. Delta, if you take WL by AE amount, here also half only if I take it, delta is WL by AE. This rectangular area is more than this triangular area. If I take this one, that rectangular area is more when compared with the triangle area. That means what? Potential energy lost is more than the strain energy stored in the member. If strain energy stored is less, potential energy lost is more, means where will the remaining potential energy go? It will go in the form of kinetic energy. So instead of applying the load W, velocity is 0. By the time it goes down by an amount of WL by AE, part of the potential energy will be stored in the form of strain energy. The remaining will be converted into kinetic energy. So after moving by an amount of WL by AE, the block weight, the weight W will have some velocity. Why it will have velocity is potential energy lost is more, strain energy stored is less. That means some amount of energy is still with the body, with the block. With that, it will go down. With that velocity, it will further go down by another WL by AE. So totally 2WL by AE. At the time of 2WL by AE comes, potential energy lost, strain energy stored will be equal. Then the block velocity is 0. Then what will happen? Because you are pulling it too much than delta WL by AE, now the energy, the strain energy stored will be more, then it will pull it back. It will try to regain its original shape. In the process, it pulls the weight W up. Then the vibration starts. Okay? Whenever there is an unbalanced force, W is downward force at the time of reversing its direction. Resistance is in terms of 2W by A stress developed. So what happens? Because of that unbalanced force in the member, that will pull the weight W. Then it compresses the member. Then it will again come down. Same process it will repeat till completely energy dissipates. By the time the weight W comes to rest, then the elongation is WL by AE only. Stress is W by A only. It will be same as that of gradually applied load. Because you applied the load suddenly, at the instant of applying the load, the deformation is 0, velocity is 0. Then it goes down by 2WL by AE, it will vibrate for some time, then stops. Wherever there is an unbalanced forces, then it will cause the member to vibrate. So it will vibrate, finally it will stop. So these are the observations you have made. These are the points that you have to remember in the exam. In the exam, you have to carefully observe Whether they are asking at the instant of reversing its direction, what is the stress, or after the vibrations are completely stopped, what is the stress. At the instant of reversing, stress is 2W by A. After the vibrations are completely stopped, then it will deform by WL by AE, stress is W by A only. Okay. So those points we will write now. This I think will remove and write the points. This we can take it as the first point. Note 1 is this one. Now having taken that point, second point is instantaneous stress due to suddenly applied load is twice that of gradually applied load. That is F is equal to 2W by A. Instantaneous means at the instant of reversing its direction, not at the instant of not at the instant of applying the load. At the instant of applying the load, deformation is 0, stress is 0. Then it goes down, then reverses. At the instant of reversing its direction, stress is twice that of gradually applied load. Instantaneous, there instantaneous means at the instant of reversing its direction. Any block, when it reverses its direction, at that instant velocity has to become 0. Without becoming velocity 0, it cannot reverse. That's what you have studied in engineering mechanics also. At the instant of reversing its direction, its acceleration is like that you will study. You have studied. So, like that. Similarly, third point, instantaneous elongation due to suddenly applied load is twice that of gradually applied load. That is delta is equal to 2WL by AE. This twice you are expected to remember. Then strain energy is how many times more? That means instantaneous. Instantaneous strain energy. That means at the instant of reversing its direction, what is the energy stored? Instantaneous strain energy stored in the member is 4 times more than 4 times more than gradually applied load. So energy stored means 4 times more. Next. Fifth point is when the load is applied suddenly, it will vibrate. Now after the vibrations are stopped, stress and strain are same as that of gradually applied load. So fifth point is this one. When the load is applied suddenly, the bar vibrates After some time, vibrations will stop. Maybe after 5 seconds like that, vibrations will stop. Now, after the vibrations are stopped, stress and elongation or top I remove. Stress and elongation are same as that of gradually applied load. That is F is equal to resistance by area, delta is resistance into L by AE. So in the exam, you must search for this word. Are they asking after the vibrations are stopped or before? At the instant of reversing its direction. Accordingly, you should answer whether it is 2W by A or W by A. Because in one of the IAS papers, they have asked this point. After the vibrations are stopped, how much? Okay, but we should have clarity about that. What is instantaneous means, and at the time after the vibrations are stopped, or before at the time of vibrations itself, what is the stress and deformation. Okay, this is about the cases when the loads are applied suddenly. Load applied suddenly means the entire load is applied to the body with zero velocity. At the instant of applying load, its velocity is zero. But if you drop the same weight from some height W, some height H say, then before striking the member, the weight will have some velocity. If it strikes with some velocity, then we call it as not suddenly applied load, we call it as impact. Now that fourth point we will see. Impact loads, how the uh, expressions change. Now let us see the fourth concept, impact. Impact means, what is the impact meaning? Definition is the dynamic action of a moving load. Dynamic action of a moving load is called impact. A moving load, whatever dynamic effect it produces, we call it as impact. Strain energy stored due to impact loading is given by, again, U is equal to area of load versus deflection curve. Now in this case, we take a case like this. This the length of the member is L, cross sectional area A. Now you drop it from some height. This is a load W. This height, let us say H. Now this weight By the time comes here, engineering mechanics you have studied, that it will have a velocity of square root of 2gh. How? This what you have studied. Final velocity square is equal to initial velocity square plus 2as. So initial velocity here 0, final velocity v square is equal to 0 square plus 2gh, and v is equal to square root of 2gh. So this block of weight W, just when it is about to hit the bar, the block will have a velocity of square root of 2gh, and with that velocity it hits. That dynamic effect is more than the more than the suddenly applied load, more than the gradually applied load. So accordingly, the deformation characteristics also are totally different. For that matter, weight is same. Depending on how you apply the load on the member, the deformation characteristics, stress characteristics are totally different. Supposing that, as here physical example if you want to see, I am standing here, say, you take a 10 kgs weight of the stone, make it into powder, keep it on my head. Some pain will be there. At the end of 10, gradually you are putting first 1 kilo, 2 kilos, 10 kilos you have kept it. So at the end of 10 kgs, some pain will be there on the head, some bearable pain. Someone keeps suddenly some 10 kgs they keep it on my head, say. Pain will be suddenly, pain will be slightly more. That pain will be 2 times, if at all you scale it, 2 times will be there. Same 10 kg stone, go to a third floor and from there you drop it. You hit it on my head. Then my head may break or severe pain will be there. That how much pain, it will be more pain or less pain depending on how you throw stone on my head. Same thing here also. If you keep that weight W at the greater height and drop it, then the deformation and the stress, in this case the effect is the pain, the deformation is it may break or it may compress. So those deformation and stress strain characteristics will be more. In this case, when you apply the load with impact, this deformation is more than 2WL by AE. Stress is also more than 2W by A, because it has some dynamic effect also additional. Steel structures you will learn that to account for that additional effect because of the dynamic action, the IS 800 gives you the impact factors. Those impact factors, if you multiply with the load, you will get the additional equivalence of the load. That means equivalent effect of a static load you will get. Impact factor sometimes you take 1.25 or 1.5 like that. That means 25% load extra you have to apply on the members to get the equivalent dynamic effect. So in the gantry girders in the design of steel structures, we will see that if impact factors how much. Railway bridges also we will see how much impact factor, so that how much impact load we have to add. Now let us see here. This is the case. Load versus deflection curve. What is the deflection curve is? When you apply load W, H it will come down, and this value is delta, let us say. And this delta is more than 2WL by AE. This is the starting point, this is the ending point. How much load W has moved down, deflected? W into H plus delta. Now this value is not delta, this value is H plus delta. What is the potential energy lost by the weight W is W into H plus delta. That means this is H plus delta up to here. This height is W. So W into H plus delta, you will get potential energy lost. Potential energy lost by weight W. And now strain energy stored. See, in this case, deflection of the weight W is H plus delta. Then what is the deformation of the member? Only delta. That much difference is there between the two wordings, deflection and deformation. So it deflected H plus delta, or it moved down by H plus delta, but bar deformed only delta. So W into H plus delta is the potential energy lost. This is the strain energy stored. After it hits it, how the deformation will be? Deformation initially at the time of hitting, deformation is 0. Then it goes down by delta, then it reverses it pushes the block weight W up, it vibrates, then stops. Okay, so always deformation starts from 0, whether it is gradually applied load, suddenly applied load, impact load, this curve will not change for a linearly elastic material. Linear elastic material means resistance versus deformation is proportional. Load versus deflection curves are also proportional, if at all it is in touch with that. So this is resistance again, AE by L into delta. This is how the deformation. Then load versus deflection curve is also area of the strain energy curve. So how much you will get? U is equal to W into H plus delta. This is potential energy lost. Must be equal to this area also, potential energy, then half delta into AE by L into delta. This is strain energy stored. Whether it is gradual or sudden or impact, these two expressions must be equal. Now, if this is second order equation, because delta square is there, delta is there, H is there. So, you will get like this. U is equal to W into H plus delta is equal to delta square by 2L into AE. So, some K into delta square, some K1 into delta square, K2 into delta plus W into H is constant. So, it is a quadratic equation. So, solving for delta, you will get that delta, we call it as instantaneous elongation. Is equal to, if you calculate that value, static elongation plus square root of static elongation square plus 2 into delta static elongation into H. This what you have derived in your SM also. Delta ST means static elongation is nothing but WL by AE. Actually, when you solve for delta, you will get WL by AE plus square root of WL by AE square plus 2 into WL by AE into H you will get. That we are writing it like this. Simplified expression we are writing WL by AE. Substitute this instantaneous elongation into stress. Then F stands for instantaneous stress. You will get W by A into 1 plus square root of 1 plus 2 AEH by W into L. This you will get like this. Delta is equal to WL by AE. Now, W by A is equal to what I can write, delta into E by L. So, delta means you write this one, delta static plus square root of delta static elongation into H into E by L. If you simplify this, you will get like this. This W by A we call it as instantaneous stress. Okay. This value is more than 2WL by AE. This delta instantaneous elongation or instantaneous contraction, whatever way you call it, is more than 2WL by AE. In case, if the height of drop becomes 0, height of drop becoming 0 means that H value becomes 0 say, then your impact load becomes suddenly applied load. If H is equal to 0, impact load becomes suddenly applied load. Then what happens, you see, delta instantaneous stress you will get or instantaneous elongation. you will get how much? Delta static elongation, delta st plus square root of delta st square plus 0. So 2 times delta static elongation. Static elongation means as if the load is applied statically, when it is, means gradually. Then stress will become instantaneous stress. You will get W by A into 1 plus square root of 1 plus 0. So you will get 2W by A. Same as what you have studied in the earlier concept. So you can apply a load on a member gradually, suddenly and with impact. In the exam, if nothing is mentioned, it means that you applied the load gradually, and accordingly strain and is stored in the truss members, etc., or frame members we have to calculate, assuming that all the loads are applied gradually. Okay. So with this fundamental, you have studied. I will take now the sixth concept. Next, fifth point is, here in strength of materials you have studied Maxwell's reciprocal deflection theorem and also the Bette's reciprocal work theorem. Those two theorems are based on this energy fundamentals, how we calculate the energy. And those two theorems are applicable to linear elastic materials. Linear elastic materials means the stress must be proportional to strain, then it is called linear. Elastic means when you apply load it deforms, remove the load it will go back to its original position. They are linear elastic materials. If you have a non-linear elastic material, say, non-linear elastic material means many ways of non-linearity will come, but elastic material only. Apply load, it deforms, remove the load, it will come back. Non-linear elastic means it can be material non-linearistic, non-linearity can be there, geometric non-linearity also can be there. That means for the non-linear elastic material, non-linearity may be whatever may be the reason, because of the geometry changing its dimensions or because of the stress strain curve may not be linear. So if they are non-linear, you cannot apply those two theorems. They have to be linear elastic materials only. Maxwell's reciprocal deflection theorem and Bette's reciprocal work theorem. Since that is already covered, we will give you this one. Maxwell's reciprocal displacement theorem and Bette's reciprocal work theorem are applicable to linear elastic materials only. Okay. Next, you have here you will learn Castigliano's theorem 1. These theorems are based on those fundamentals only, assuming that the loads are applied gradually and energy stored we know how to calculate, and that energy, how the materials behave, based on that these people have proposed some theorems. Castigliano's theorem 1 tells you that if you want to find the resistance at any point, the first derivative of energy with respect to displacement at that point gives you resistance at that point in the direction of the displacement. That means how much was the resistance developed in the member. So that resistance may be equal to the applied load. So this is what the theorem 1 tells you. The first partial derivative of strain energy with respect to displacement. Why partial derivative with respect to displacement is, in a structure displacement maybe 10 displacements are there, delta 1, delta 2, delta 3, delta 4, like that. 10 displacements at 10 different locations. If you differentiate the total strain energy with respect to first displacement, say, then you will get the resistance at the first displacement location only. Like that. That's why it is called partial, because displacements can be many. The first partial derivative of total strain energy with respect to displacement at any point in a structure gives resistance at that point in the direction of displacement. This theorem 1 deals with the deformations and resistances, not applied load, the deflection. Okay. So this theorem applicable to, it is applicable to linear and non-linear elastic structures. Linear or non-linear, but elastic structures only. Inelastic structures you cannot apply any theorem at all. It must be elastic. Maybe linear elastic, non-linear elastic, but it must be elastic structure. So this is applicable to linear and non-linear elastic structures. Okay. Geometric non-linearity we don't consider in the theorem 1. I think in strength of materials some examples also you have studied, non-linear cases. Now you have theorem 2. This is used in the stiffness method of analysis. It is useful in stiffness method of analysis, or it is used that way. Then you have another theorem called Castigliano's theorem 2. What it tells you is delta is equal to dou u by dou w. First derivative of energy, this is now potential energy we call it. We take it as potential energy or complementary energy. Okay. with respect to load at any point gives you displacement at that point in the direction of the load. Since you are writing energy in terms of loads, we call it as potential energy. Okay, so the textbooks we see that U as the complementary energy. For linear elastic materials, complementary energy, potential complementary energy and strain energy are equal. So whether you write strain energy or complementary energy, both expressions are same. But to be precise, here you are writing complementary energy, here it is strain energy. If you have a linear elastic material, complementary energy, strain energy are equal. But if you write that complementary energy, means if you write that in terms of the loads, then that we call it as the complementary energy. Generally, complementary energies are written in terms of applied loads. Strain energies are written in terms of the displacements. Okay. So when you want to use Castigliano's theorem 2, your energy you have to write in terms of the applied loads. Okay. Then that energy with respect to, if you differentiate it with respect to load, you will get the displacement in the direction of the applied load. Why partial? Maybe there can be WPQ like that forces, and energy you calculate due to WPQ all. Then due to W alone, what is the displacement you want to say? At W location load, differentiate energy with respect to the load. Then you will get displacement at the application of the load W only. Like that. Q you want to say, at the location of Q, what is the displacement? Then first derivative of energy with respect to Q, you will get displacement of the structure at the location of Q only. So, this is the theorem 2. The first partial derivative of complementary energy, that is energy written in terms of loads, derivative of complementary energy with respect to load at any point in a structure gives displacement. Gives displacement in the direction of the load. This theorem, because you are writing it for the in terms of complementary energy, this theorem is applicable to only linear elastic materials. For nonlinear elastic materials, this form of energy expression in terms of W, if you write it, it won't work. You cannot apply. Okay. So, Castigliano's theorem 2 is applicable to linear elastic materials only, where complementary energy, strain energy, both are equal. Okay. Now, with this understanding, now we will take up this theorem is useful in flexibility method of analysis. In flexibility method of analysis, you will write energy in terms of the loads. That means complementary energies you will write there. Then you differentiate it with respect to loads. Whereas here, the stiffness method you will write strain energy in terms of the deformations. We will see in the matrix methods of structural analysis how the energies expressions should be written. Okay. Now, this is about the fundamentals regarding Castigliano's theorem 1, theorem 2, and Maxwell's reciprocal and Betti's reciprocal work theorem. Now, with this understanding, how we should apply? Now, you see, this explanation, if you want, it goes like this. You, you see, you are writing in terms of the displacement, say, delta square by 2E into A into L. We have to remove this part, delta square. This you have to cut it for 2 minutes. Earlier one you have to cut it. 2 minutes, I think in the editing we can. Now you see example I am taking. Strain energy U is equal to delta square by 2L into AU we have written. This is the energy stored in terms of the deformations. Now if you want to find W, resistance, is equal to first derivative of energy with respect to displacement. Delta square means what you get? 2 delta by 2L into AE. So you will get AE by L into delta. So this is what I have told you, resistance means AE by L into delta. So like that resistances you will get, if delta becomes 1 say, then W resistance becomes stiffness coefficient. This is the, we use it in stiffness matrix method. This type of analysis we use in the stiffness matrix methods. If delta becomes 1 means what? If delta is equal to 1, AE by L. Strength of materials sir also told you, AE is the axial rigidity per unit length is axial stiffness. So you get stiffness if delta becomes 1. That's why this theorem 1 is useful in the stiffness methods of analysis. Similarly, if I write delta in terms of load, that energy we call it as complementary energy also. This is W square L by 2AE. This is complementary energy now. Now, first derivative of delta is equal to dou U by dou W. How much you will get? 2W into L by 2AE. So, you will get WL by AE. If W becomes 1, then delta becomes flexibility coefficient. This type of analysis we use in the flexibility matrix methods. So theorem 2 is useful in the flexibility matrix, flexibility methods of analysis. This energy you will use it in the stiffness methods of analysis. Okay. So that's how theorem 1 and theorem 2 are. With this understand, now this theorem 1 we will see in the stiffness matrix methods. Now we will take up this one. We will write energy in terms of the applied loads, then that means complementary energy we will write, then differentiate it to get the displacements in the trusses. Now let us see applications of Castigliano's theorem 2. Now, to find application, the where you are using this Castigliano's theorem 2 is first application. To find absolute deflection of a joint. Now you see, instead of taking a single rod, now we will take a truss where all members are subjected to axial forces only. Let us say A, B, C, D, E. You are applying some load W, say. Earlier in the energy stored due to gradually applied loading we have seen, you applied load W, then resistance is also W, then that means resistance you write say P, then P becomes W only, like that. So only one member you have taken, energy stored is W square L by 2AE for single member. Now instead of one member you have one truss. In a truss there are 7 such axially loaded members we have taken. So if you have 7 members, energy stored in the structure means individual strain energies you can add to get the total strain energy in the structure. So we will now calculate U. U is equal to strain energy stored in this structure. Now how will you calculate? Due to the applied load W, member forces we can find. See, this is like a simply supported beam. Simply supported truss behaves like a simply supported beam. In a simply supported beam, when you load it, all top chord is under compression. Here also all top chord members are under compression. Let us say this force is P1, P2, P3. In a simply supported beam, bottom chord is under tension when loaded, bottom fiber is under tension. So similar to that, in a simply supported truss, all bottom chord members are under tension. P4, let us say P4, P5, okay, like this. Now these two members, when I am holding and pulling it down, and these two members have a resistance upward like this. P5, this is P6, P7. These two must be tension. Like this, by inspection itself, the arrow marks for all forces in the members we can find. Except very few cases, almost all cases we can find by inspection itself whether force in the member is compression or tension. So forces you found. Now this P1 means as the load W, applied load W is gradually applied. As the load varies from 0 to W, forces in the members will vary from 0 to P1, 0 to P2. Like that 0 to P2 it will increase. That means these are the forces, resistances developed within the member due to gradually applied load W. So now you are writing in terms of the forces like this, say. Strain energy stored in the structure, summation of P square L by 2AE. P means force in the member due to the applied load W, where P is equal to P1, P2, etc. Forces in all members due to applied loads W1, W2, etc. Here I have shown only W, it can be W1 due to W, W1, W2, maybe W1, W2 also there, say, like that. L means L1, L2, etc. Lengths of all members. Okay. Now energy stored you will get. Now from Castigliano's theorem 1, what we can write? From Castigliano's theorem 2. Displacement delta, vertical displacement of giant E if I want, first derivative of energy with respect to load at that point. Delta VE means vertical displacement at E. Vertical displacement at E, dou U by dou W. First derivative of energy with respect to load at the point of where you want to find the displacement. Now what we will get it here? Delta VE is equal to dou U by dou W means you differentiate that P square. P square means 2P, and P differentiation with respect to W you have to write L by 2 AE. Why we should write is because in this case I have shown only W, but there can be W1, W2, W3 also. Many loads can be there. Out of all the loads, if you differentiate with respect to W, you will get delta VE. At C W2 is there, say, then dou U by dou W2 will give you displacement at C, like that. So that's why it is partial differentiation. This value we will write it as summation of P, will keep it as it is, 2 cancels out. Dou P by dou W meaning is K into L by AE, where K is equal to K1, K2, etc. K1 means dou P1 by dou W, dou P by dou W, etc. That means the meaning of derivative of P1 with respect to W, meaning is if at all you apply unit load at the location of W, K1 means the force in the member due to unit load. Okay? So K1, K2, etc. is equal to forces in all members due to unit load applied at a point where we want to find a displacement. What it means is the explanation part of it. Assume that we have a simple example I am giving. Assume that you are applying, say, some load W. This member, say, A, B, C. This angle of inclination, let us say 45 degrees. Okay? Now, due to W, I can find force P in this member, tension. Let us say this value P1. Force in the member AB is P1 because of the load W. Then how much is the P1 value? P1 sine 45 is equal to W. That P1 means W by sine 45. So W root 2, or in other words root 2 into W. Then the force in the member AC. The x component of this, if I see, P1 cos 45 is going left side. To balance it, this force must exert right side. If this is going left side, this should go right side. Otherwise, sigma x0 will not happen. So P1 cos 45 means root 2 W cos 45, P2 you call it, it becomes W. Towards the joint, towards the joint. For such cases, again sigma y0, then P1 sin 45 minus W is equal to 0, then P1 is W by sin 45 is equal to W by W root 2. That much story we should not write by inspection. P1 sin 45 is W, so P1 is W by sin 45, so root 2 W should be right. So root 2 W cos 45 is acting left, so right side is W. So once here towards joint, here it should be towards the joint. So now you see here, what's the meaning of this force differentiation with respect to W? So dou P1 by dou W, you will get root 2. Dou P2 by dou W, you will get 1. Differentiation of W is 1. This result you will also get by taking simple case we have taken instead of taking multiple loads and differentiating. 1. This one, it has no units. Why it has no units? You see here root 2 W Newton, W is also Newton. So Newton by Newton root 2. Root 2 has no units. Since it has no units, your 1 also should have no units. Then equivalency satisfies. 45 degrees say. So this is down, this point let us say A, B, C. This is down, so it has to be up. Now this value we call it as K1, away from the joint, away from the joint. So K1 sin 45 is 1, K1 is root 2. If this is root 2 acting left side, this should act right side towards the joint, towards the joint. Now K2 becomes 1, root 2 cos 45 is 1. Okay. Now observe this one carefully, this and this. Dou P1 by dou W is nothing but K1. Dou P2 by dou W is nothing but K2. Like that. The meaning of dou derivative of P1 with respect to W is equivalent to applying unit load at W location, finding the force in the members. This way, that's why since you are using strain energy concept, this is called strain energy method of analysis. Since you are replacing that dou P by dou W as a unit load, we also call it as unit load method. Okay. So this is the first example. So PKL by AE. This is deflection at any point, means you have 3-step procedure. First step is P, find forces in all members due to the applied load. Second step is this one, K, due to unit load what are all the forces in the members. When unit load is applied, that actual loads should not be there. So this K value. Then in the third step, multiply them, PKL by AE. These 3 steps, finding P, finding K, finding PKL by AE, must be over in 2 minutes time. To ensure that you will complete it 2 minutes time, they don't give more than 2 members or 3 members. Only then your stipulated 2 minutes time you can complete. So this is your first application. Then second application, is to find the relative displacement of any 2 joints. Second application, to find relative displacement of any 2 joints B and E. Now we will see this point, let us say A, B, C. Here you are applying some load W, D, E, F, G. In the first example explanation, I applied a load W. At that location only I tried to find the displacement. So dou E by dou W we have written. It is not necessary that wherever you applied load, there only I can find the displacement. Load can be at one location, your displacement finding location can be some other location. Such cases, in this case you see, load is applied at C, I want to find displacement at B say. Then displacement at B, if I want to due to this load W, there is no load here. I cannot use Castigliano's theorem 2. Theorem 2 tells you that in a structure, if you want to find a displacement at any point, there must be a load. If load is not there, as in the strength of materials, you have to take a dummy load whose magnitude is 0. And it is not necessary that I should find vertical displacement only. I can find inclined displacement also of joint B. Now I want to find displacement of joint B not vertically down. In this direction I want to find say. Then in this direction I have to apply an imaginary load Q whose magnitude is 0. Then due to W and Q I will find first P values. And in the strain energy when you are finding all the loads that you are expecting to act, you must apply them simultaneously and calculate the deflection or calculate the energy. First apply load W, find the strain energy. Then apply load Q, find strain energy. Add individual strain energy is not possible. Because strain energy U is equal to W square L by 2AE. W has power 2. So when you apply first load, then say it goes 0 to W say. Then 0 to P. Second time when you are taking 0 to Q, you are applying. Then that load also starts from 0 to Q. Energy stored will be totally different. If all the loads are applied at once, increased gradually to their respective magnitudes, the forces what you get and energy you get is P square L by 2AE, then you will get the correct strain energy expression. Otherwise, two times when you apply loads individually and get the values means not possible. Because first time when you are applying loads, it will go from 0 to W, remove the load. Then second time when you apply, again that starts from 0 only. But whereas the energy expression when you are calculating all the loads when you apply at once, only one time they start from 0 and go to their respective values. That's all. So only one time they will reach their respective magnitudes. But whereas individually when you apply 0 to W once, 0 to P1 once, 0 to X1, 0 to X2 like that, every time it starts from 0 only. Energy what you get in that manner is very less when compared with the energy you get when all loads are applied at once and increased gradually. Okay. So now that point in strength of material search might have told you in many places. So again we don't discuss. Principle of superposition you cannot apply when you are finding the strain energy. Now that's why when you are applying now WQ simultaneously at once, you are increasing their magnitudes. In this case Q value is 0 itself. Okay. So now due to W and Q, find forces in all members. That is called P values. Relative displacement means that. So P values you will calculate. Then remove W, Q remove it. Apply unit load in the direction of Q like this. Find forces in all members. You call it as K1 values say. So then displacement of B you will calculate. Displacement of B is equal to first derivative of energy with respect to not W with respect to Q is nothing but summation of P into dou P by dou Q you have to write into L by AE. This value let us say summation of P into K1 into L by AE. K1 means forces in all members due to unit load applied at B in the direction of BE. Some value you will get. Next. This problem is over. You get that value, let us say delta B, 10 mm you got it say. Now Q and 1 you take it, throw it out. I want to find a displacement of E in the direction of EB. Then what we have to do, this is now not there. Instead of drawing a different problem and wasting the time, same problem I am showing. Now I want to, this is now not there. Displacement of E I want to find in the direction of EB. So I have to apply a force S whose value is 0. So now delta E means first derivative of energy with respect to S. So summation of P into dou P by dou S into L by AE. This you will get summation of P into K2 into L by AE. Some values we got it, say. P means forces in all members due to applied loads W. K2 means forces in all members due to unit load applied at S. Dou P by dou S means due to unit load applied at E. That means here you have to apply a unit load and find the K2 values. So now you got, you calculated that value, let us say. Displacement of E, you got it as say 8 mm. Now what is the relative displacement? This way 10 mm, this way 8 mm. What is the relative displacement? You should not subtract 10 minus 8 is equal to 2 mm, we should not write. Because 6th class you have studied like this. You have a train, say train A, moving right side with a velocity of 100 kilometers per hour. Another train B, moving left side with a velocity of say 25 kilometers per hour. Now what is the relative velocity? Is equal to 100 plus 25, 125 you will write. Similar to relative velocities what you have studied in 6th class, here also now you are telling relative displacements. This is 10 mm, this is 8 mm. So relative value is 10 plus 8. So relative displacement of P and E in the direction of BE is nothing but delta B plus delta E is nothing but summation of P into K1 plus K2 into L by AE, because the P value is same, L value is same. So I will write delta BE is equal to summation of PKL by AE. Now instead of calculating two times separately and wasting our time, first apply unit load, find the K1 values. Then remove them, then apply unit load, find K2 values. Then add individual forces K1 plus K2. Say. Instead of solving them separately and again adding them and wasting the time, apply two unit loads at once to find the forces only, not to find the energies. Okay. So find the K1 plus K2 values simultaneously. At once we will calculate to save time. So if you want to find the relative displacement of any two joints in the direction of you apply two unit forces in the opposite direction, not in the same direction. Then you cannot add them like that. You have to subtract. Subtraction now is not possible. Then you have to calculate separately and subtract. Addition means you can simply two forces you put it, add it. So apply two unit loads at once. Find the K values. That K values is because of this load and this load together. That's what that expression tells you. Then this is the process now to find relative displacement. Due to W, find the P values. Due to these two unit loads, find K values. Then PKL by AE gives you the summation of the two displacements directly. Instead of individually calculating and adding and wasting the time, at once you can add them. So, conclusion. To find relative displacement of joints B and E, apply unit loads at B and E in the direction of BE. and find forces in all members. This we call it as K values. Then delta BE is equal to summation of PKL by AE. See, formula is same, PKL by AE, but finding K values is different. Earlier, to find single displacement also, formula is PKL by AE, where K is forces in all members due to single unit load. If you want to find relative displacement, PKL by AE same formula, but K is forces in all members due to two unit loads, where P is equal to forces in all members due to applied loads W1, W2, etc. K means forces in all members due to unit loads applied at B and E. In the direction of BE. This is your relative displacement concept. Next, to find the rotation of a member, another third application is how much the member GF rotates you want to find, say. That also we can we can find using Castigliano's theorem too. Okay. Now let us see the third application. This I remove. To find rigid body rotation of any member GF. So this I remove. Okay. To find the rigid body rotation of the member GF we want to find. This I remove. First we should know why we used that word rigid body rotation. Supposing that you have a simply supported beam, say. In strength of materials you have studied W, this is A, B. Now, due to this load, it will deflect like this. In SM, you have calculated theta also, theta A. And you also know what is the bending stress developed here. Bending stress. So, the simply supported beam rotated by theta A after developing a bending stress of M by Z. So, after developing a stress, if it rotates, it is not called rigid body rotation, it is rotation after deformation. It is not a rigid body rotation. Because beam rotates by theta after developing a bending stress. Then what is rigid body rotation? Supposing that you have a simply supported beam. Due to some reason, one of the support sinks down. Load is not there, support sinks down. Why support sinks down? Due to some soil problems below this column, maybe soil liquefaction of soil may have taken place. So this is the delta. This is called sinking of supports. Now you see, what's the bending stress at any location? Straight line will be there. It is a simply supported beam like this. If one of the support sinks down, you see, there is no bending stress here, simply rotates. That rotation, we call it as rigid body rotation, theta A. This is rigid body rotation. Beam rotates by theta without developing any bending stress. So rigid body rotation. So conclusion is, without developing any stress, if a member rotates, it is called rigid body rotation. Now this is rigid body rotation, no bending stress. Now why we are calling here as rigid body rotation is coming to this problem. This member GF, there is no bending moment as we have already studied. So, but it will rotate. Why it will rotate? Now when you apply load here, downward load, deflections, G comes down, F comes down, E comes down, B will come down, C will come down. But how much they will come down, the magnitudes are different. If G comes down by 2 mm, say, central deflection is more, maybe 5 mm. See here, it is like this, say, G here, F here. Initially it is like this. After load is applied, G will come down, F will come down more. Then that means the member will no longer be horizontal, it is slightly inclined. That is called rigid body rotation. That you will find it from from Castigliano's theorem too. So having understood rigid body rotation, how it looks like. Now you see, this member GF length, let us say A. This I will show it here. G, F distance is say A. How much it rotated we want to find. For that what we do is, first you apply, due to W, find forces in all members, P values. Then here apply unit load 1. Due to unit load 1, find K values. So P KL by AE, you will get displacement of G in the direction of unit load. So that one, assume that it went up by an amount. We don't know whether it is going up or down. So G goes to G dash say. So delta G you calculated. Maybe delta G 5 mm, let us say you found it. So issue is over. Now take this unit load, throw it out. Fresh problem. I want to find displacement of F in the downward direction. Okay. Apply unit load. Now this is not there. Due to W, find P values. Next fresh problem started. Due to 1, find K values, forces in all members. So PKL by AE, you will get displacement of F in the direction of unit load. Assume that that also you calculated and you got it this way. F comes to F dash, this is delta F. This is say 3 mm, this is say 5 mm. Some calculations you got. Now this went up, this went down. This is your final position of the member. G goes to G dash, F goes to F dash. Blue color is initial position of the member before applying load. After applying load, G dash, F dash is the member position say. Then how much it rotated? This value is theta GF. How much you will get for small values? This is how much? Delta G plus delta F. So, you will get tan theta GF is approximately equal to theta GF. Why? If theta is so small, tan theta is theta. Opposite direction is delta G plus delta F by A. So, theta GF is nothing but delta G by A plus delta F by A. I can write like this. So, this is what is the process. First apply unit load, delta G you find. Next, apply another unit load, find PKL by AE, find delta F. Then, I don't want the delta G. Delta G by A, delta F by A I want. So, add the two displacements divided by A. Instead of finding delta G separately, delta F separately, adding them separately and by A, instead of doing that, this is what my final expression. If I apply unit load, I will get delta G. I don't apply unit load, I will apply 1 by A. If I apply 1 by A, I will get delta G by A directly. To get that, it must be a linear elastic material. That's why this is applicable to linear elastic materials only. Castigliano's theorem 2. Okay, it is like this. One biscuit is 2 rupees, 3 biscuits, 6 rupees, like that. So linear interpolation. If I apply 1, delta G. If I apply 1 by A, I will get delta G by A. Here also, I wanted delta F by A. If I apply 1, I will get delta F. So don't apply 1, apply 1 by A. Then delta F by A directly I will get. I want summation also. So instead of individually applying 1 by A values, 1 by A values, 2 times separately calculating and adding, apply 2 unit loads at once. Then summation also you will get directly. So that means whatever member you want to find the rotation, apply unit couple. You see this force and this force is looking like a couple. Couple means a pair of equal oppositely directed non-collinear forces. It is called a couple. Now this is 1 by A, 1 by A, distance is A. What's the moment of this couple? 1 by A into A, 1. That means it is unit couple. So if you want to find rotation of any member GF, which you call it as rigid body rotation, apply unit couple at the two ends of the member. Then due to W find P values, due to this unit couple find K values, then PKL by AE directly gives you the delta G by A plus delta F by A values you will get directly from the principle of superposition. Now you see, this is what your conclusion. To find rotation of any member GF, comma, apply unit couple at G and F as shown in figure. These two forces form unit couple. That is, 1 by A into A is equal to 1. Unit couple as shown in figure. Then what we have to do? Find forces in all members due to unit couple within brackets, that is K values. Okay. Then rotation of member GF is given by theta GF is equal to summation of P K L by AE. Here also formula is same, but finding K only is different, where P stands for forces in all members due to applied loads W1, W2, etc. K means forces in all members due to unit couple applied at G and F. So formula is same in this case also, but finding K values is different. Here rotation means K values is because of unit couple. If you want to find relative displacement, you have to apply two unit forces in the opposite direction at both ends of the, or whatever joints you want to find the relative value. So those two unit forces must be opposite to each other, either towards or away. Then only we will get relative displacement as the summation of the two displacements. If you want to find absolute deflection of a single joint, simply put one unit load. Okay, either one unit load or two unit loads or a couple, depending on whether you want to find only deflection of a joint or relative displacement of two joints or rotation of a member. So these three applications, yeah, many times they have asked in GATE for 2 marks questions. Allotted time is 2 minutes. Number of members they give you maximum of 3 members you have to list out, or 2 members only sometimes, or 1 member only. So 2 minutes we can complete. Now we will see how we have to calculate, or numerically how we have to find them in the stipulated time. That we will see. For today enough. और कुछ क्लास है क्या अभी? Okay, now we have taken the Castigliano's theorem 2 and its applications. We found that there were 3 applications we have discussed regarding the trusses. One is absolute deflection of a joint, that is delta V, E or any point sigma P K L by AE. Formula is same, P K L by AE is same for all problems, but finding K only is different. If you are having, or if you want to find only deflection of a particular joint, then K values are found by taking unit load at that point or at that joint and find forces in all members. So delta V is P K L by AE summation. If you want to find relative displacement of any two joints in the direction of their line of joining, then you have to apply two unit loads, and those two unit loads must be at the ends of the members or wherever you two locations that you want to find relative displacement. Those two unit loads must be either towards or away from each other. You have to write. Why we should write is because we are using principle of superposition. If they are acting towards each other or away from each other, relative displacement is the summation of the effects. We can only write the summation effect. Two for effects you can only add. You cannot subtract in our formula, PKL by AE formula, you can only add them. So to add them, arrows must be towards or away from each other. Then relative displacement is summation of the two displacements. That sum directly we will get without calculating separately. the displacements and adding them. So at once we can calculate from the principle of superposition. That means that because you are using principle of superposition, it must be a linear elastic material. Linear elastic materials only principle of superposition is applicable. So that's why Cauchy-Glenow's theorem 2 is applicable to linear elastic materials only. Okay. Now, third example I have given you was the rotation of a particular member, that is called rigid body rotation. Rigid body rotation, what we have done was we have applied a unit couple at the ends of the member. Either you can apply clockwise couple 1 by A or anti-clockwise couple. When we have shown the diagram, we have arbitrarily chosen one force upward, one force downward. Then clockwise I have shown. But it is not necessary that you should show clockwise. You can show anti-clockwise couple also. But you must show such that it must form a couple. If one is downward, one is upward. Which is downward or upward is our choice. So if at all the result works out to be negative, then we will know that our assumed direction of couple is wrong. So we have to change the direction of the couple or change the opposite to the direction of unit couple. We find that rotation happening. Like that. 3 applications I have given you the fundamentals for that. Now we want to solve the problems within our stipulated 2 minutes time. In the process of explaining, it may take more time, but when you are doing on your own, when you are solving them, you will find that you will take only 2 minutes time. If you are taking 4 minutes time, then you see where you are wasting the time, you plug that. Okay. Now the problems numericals we are taking now. Delta vertical displacement of A. This is a simple trusses, 2 members or 3 members only they have to give us because of the time constraint. This is 10 kilonewton, let us say. This point A, B, C. This length is 1 meter. This length is also 1 meter. It is hinged at both ends, fixed. They cannot move upward or downward or right or left. So this is now becomes a stable structure, stable truss. That stability aspects of the trusses we will discuss again separately for all types of structures, beams, trusses and frames, under what conditions or under what circumstances they can be stable. That stability we will discuss later. Now you assume that it is a stable, statically determinate truss. Okay, 10 kilonewton was given. Now this is 1 meter, 1 meter. AE is constant for all members. This they will give either AE is constant or AE can be different. One is AE, another can be 2 AE. Strength of materials you have studied that axial rigidity AE is it is in newtons or kilonewton. It is a force required to produce unit deformation in a unit length of the bar. That is called axial rigidity. This is the problem. You want to find vertical displacement of A. First we will see what is the scope of the work involved. Delta VA, vertical displacement of A, summation of PKL by AE, where P stands for forces in all members due to applied loads. K means forces in all members due to unit vertical load applied at A. You have to apply unit vertical load at A. Only one load you have to apply, one unit load, because you are finding displacement of a single joint. This is the scope of the work. So finding the forces P value is the first step. Finding K values is the second step. Third step, multiply them. That's all. Okay. Now this is your solution. First step, P values. Now this is the applied load 10 kilonewton. This point let us say A, B and C. 1 meter means this angle of inclination is 45 degrees. Okay, both like this. Now, as last class I have given you about method of joints and method of sections. I hope all of you have understood how we have to get it by inspection itself. We should not write sigma x0, sigma y0 for each joint, then get the values. That will waste our time. That is only for the beginners. Now assume that you have already learned. Now we see by inspection itself how to fix the arrows of the forces. If this load is acting vertically down, how this member should respond? It should apply force up. Okay, like that. So what this is doing on this joint is it will exert a force like this. This you can take force in the member AC. Next, so we'll see how much its magnitude is. First we'll fix the arrows. It's going it's moving up to the right side. To the right side. To balance it, force must here should act left side. This force is FAB. Now you see, now we want to find FAC. You write for sigma y0. FAC is sine 45 minus 10 is equal to 0. So FAC is 10 by sine 45. That means 10 root 2 kilonewton. If arrow towards the joint, here also it should be towards the joint. Next, this one. 10 root 2 cos 45, that is plus, minus FAB is equal to 0. That is sigma x 0. So 10 root 2 cos 45 is acting right side. To balance it, this should be left side. 10 root 2 cos 45 again means 10 kilonewton. Here arrow is away from the joint. Here it should be away. That's all. This you don't have to explain in the rough work also. Simply 10. So 10 root 2 balance. Then x direction 10 root 2 cos 45 right side means 10 right side, 10 left side. Issue closed. Then second step. K values. Now you have to apply unit load 1, and this 1 has no units. It has no units. This point you take say A, B and C. This angle of inclination is 45 degrees. Now you say again we don't have to strain ourselves to find what the forces are. Linear interpolation. If you apply 10, 10 root 2. If you apply 1, 1 root 2. So this value is 1 root 2 means root 2. No units, simply root 2, that's all. Towards the joint, towards the joint. If you apply 10, force in this member is 10. If you apply 1, it should be 10. Away from the joint, 1. Say it takes around 10 seconds time. This around 15 seconds, 10 seconds, 25 seconds time. Next, the other you cannot save the time, you have to list the members. So third step, we will write it like this. Delta vertical displacement of A is nothing but summation of P, K, L by A, E. So first we'll write entire thing, we'll table it out, then whatever time you can say we can write. Member, then P, then K, then length, then delta VA, summation of P, K, L by AE. In this one, this is a sign convention. Tension you take positive, compression you take negative. You don't want it, tension you can take negative, compression you can take positive. Our choice. Whatever way you choose, which is whatever you want to take positive or negative, that will not influence your end result. Now you see, first now list out the members. First we will take say member AB. Member AB is this one. Force in this member is tensile, so plus 10. K values. AB member, again arrow mark is away from the joint, so plus 1. Length of the member 1 meter. PKL by AE, that means 10 by AE. That's all. Next, AC member. AC member 10 root 2 compression, so minus 10 root 2 kilonewton. This is also compression, so minus root 2. Then what is the length of AC member? LAC. Square root of 1 plus 1. So you will get root 2 meters. Now, this is root 2 meters. PKL by AE. 10 root 2 into root 2 is 20. 20 root 2. 20 root 2 by AE. So 1.414. So 28.28 by AE. These are individual contributions of the members to the vertical displacement of joint A. Since all of them are connected, total contribution is so much. Delta VA is equal to 38.28 by AE. Okay. Now here positive sign indicates that our assumed direction or indicates that, we will write it like this, indicates that delta VA acts in the direction of unit load. That is, delta VA is downwards. See, a positive sign indicates it acts in the direction of unit load only, not in the direction of the load, applied load. Sometimes what happens, load is at one location, displacement at some other location you are finding, say. At that some other location, some unit load direction, whatever you are giving it, in that direction only displacement will happen, wherever may be the applied load. That's why positive sign indicates that delta VA acts in the direction of unit load only. Whatever direction you give it for unit load, in that direction it acts if it is positive. Negative means opposite to the direction of unit load. So this is how you will find the vertical displacement of joint A. So first step, P, K values you must complete in 30 seconds time, because you should not write by writing here sigma x0, sigma y0, then finding this one 10 sine 45 plus 10 sine plus f sine 45 minus 10 is equal to 0, f is equal to 10 by sine 45, then one more line 10 root 2. If you write like that, problem is gone. You should be able to get it. F sine 45 is 10, f is 10 by sine 45, so 10 root 2. So 10 root 2 is this, whose x component is 10 root 2 cos 45, right. Cos 45 means 1 by root 2. So root 2 cancels out. So 10. So 10 right, so 10 left. Like that. By inspection. Then for 10, 10 root 2. For 1, 1 root 2. For 10, 10, 1, 1. Closes. Then that. PKL by A. Small table will make it. You have 2 minutes time for this problem. We can complete. Okay. Now if you want to, here vertical load is there, vertical displacement only we asked. It is not necessary that in the load direction only we have to find the displacement. They can ask you displacement of A in x direction also. Then how to manage? What are the changes that we have to make it? Let us see. Now second question. Delta horizontal displacement of A. Delta HAC. A is constant for all members, now not required. Now this is the change. Instead of delta VA, we will write now delta HA. Formula is same, P same, but K is forces in all members due to unit unit horizontal load applied at A. Okay, this is the scope of the work. Now come to this one. Solution. First step, P values same, no change. K values, they are because of the unit horizontal load. So you have to apply unit load here, 1. This one has no units. So if one is acting right side, what are the forces? That you have to find now. Okay. Now you see, K values we are finding now. Unit load is here. Now you see, at A, 2 members are there, 1 force is there. Whether members are there, forces are there, it doesn't matter. Total number must be 3. So here, this is a member you can visualize. That member whose force is 10 kilo is 1. Now 1, 2, 3 members are meeting at A. Out of these 3 members, 2 are in line with each other. Force in the third member is 0. Next here, one right side, to balance it, it should be left. First you have to put like that. Put arrow mark left, right 1. Next, now this arrow is away from the joint. Here also arrow must be away from the joint. Okay, so this K1 will not change, but other it will become 0 for the horizontal displacement. This is one change. Then third step, delta VA, now you replace it by delta horizontal displacement at A. Formula is same. Tension positive, compression negative. This we have to change. Delta horizontal displacement of A. Then AB. P value is 10, K is 1, length is 1, 10 by A is same. AC member. You see here, AC member, what happens in this second table? AC member P value is 10 root 2 minus 10 root 2. K value 0. Length whatever it is, this value now becomes 0. Okay, these are the changes if they ask you horizontal displacement. Now you see, delta HA, when you sum them up, you will get 10 by AE. Here again, positive sign indicates that delta HA acts in the direction of unit load. So, delta HA is rightwards. Like this it will run. Okay. Now, what is the meaning of getting 0 here? The implied meaning of 0 here is, if at all in the table 1 becomes 0, the contribution of this member to the horizontal displacement of A is 0. It will not contribute to the horizontal displacement. If at all joint A moves to right side, because already BC member whatever it is elongating, it will simply facilitate that elongation, that's all. It will not add to it in any way. That is the meaning of getting the 0. Okay, so this is about the horizontal displacement of joint A. Anything you will calculate like that. Now let us see the second application. Second application is that relative displacement. How to find relative displacements? This I remove now. This is what we just briefly review what we have learned in strength of materials. Note 1. Axial rigidity. How axial rigidity looks like? Is it a stress or a deformation? You see here, you will study like this. Delta, you have studied this one, delta is equal to PL by AE. Then AE means PL by delta. Now, supposing that if delta is equal to 1, length also will become 1 say, then AE becomes P. That means axial rigidity means it is the load required to produce unit deformation in a unit length of a bar. That force we call it as axial rigidity. Assume that you have say pen like this pen length is say 10 centimeters. Hold it, pull it like this. How much load you have to apply so that this 10 centimeters length will elongate by another 10 centimeters. That load required is called axial rigidity. If at all we assume that it is till that time it is in the proportionality limit or elastic limit state. So that load gives you that load we call it as axial rigidity. Okay, axial rigidity. This definition is like this. It is the load. It is not the stress, not a deformation. It is the load required to produce unit deformation in a unit length of a bar. Okay. Then second point. This what you have studied, delta V A we have learned, summation of P K L by A E. Now you see you have to find first P values, then K values, then multiply them and waste the time. To save our time, they will calculate PL by AE value for each member. Calculate say delta values, deformation of each member they will give us. Then I can write it as summation of K into delta. This we can write where delta stands for PL by AE for each member. When you will write deformation PL by AE, if at all loads are applied, then PL by AE is the deformation of each member. So, if loads are applied, this is the formula. This is what you have studied PL by AE. Strength of materials, next chapter we have studied about the temperature stresses. Any change in the temperature in a member also produces elongations or extension or expansion or contraction. They also are considered as deformations. If at all temperature changes are given, you will write alpha TL for each member. This you will use it if temperature changes are given. Castigliano's theorem 2 will not worry the cause of delta. Whatever may be the reason that delta is happening, the theorem 2 will not worry. Simply K delta we can write. Now we have taken delta is PL by AE for each member, alpha TL for each member. It can also be due to lack of fit. Delta can also be due to lack of fit. That means a member you are supposed to cut it, say, as you have seen in this problem, length of inclined member is say root 2 meters. Root 2 meters means what? 1414 mm. But exactly 1414 mm you may not be able to cut, or welder may not be able to cut. Say 14 mm short he cuts, say. Then that 14 mm is the delta. Delta short means delta mm you can take it as a contraction. So that delta can be due to lack of fit, due to temperature changes or due to applied loads. The reason why the delta happened, theorem 2 will not worry. It will give you displacement of a point in a structure directly. Okay. Then what is this alpha? alpha for steel 12 into 10 to the power of minus 6 mm per degree centigrade. We have studied that coefficient of linear expansion alpha is for steel is 12 into 10 to the power of minus 6 mm per degree centigrade. What is that coefficient of linear expansion represents? See here, mm per degree centigrade means you have to read like this. For 1 degree centigrade variation in the temperature, 1 length of the bar will change by 12 into 10 to the power of minus 6 That means this is the change in length by original length. Change in length by original length. That means this is a strain. Strain for 1 degree centigrade variation in the temperature. That means alpha represents strain for 1 degree centigrade variation in temperature. Then if alpha represents strain for 1 degree centigrade, for T degrees centigrade variation in temperature, strain small e, how much will be? For 1 degree alpha is the strain, for T degrees alpha into T. How? We have studied in our second class, if one biscuit costs is say 2 rupees, 3 biscuits will cost 6 rupees. If we know this simple logic, 1 biscuit 2 rupees, 3 biscuits 6 rupees, 50% of strength of materials is over, everywhere same thing only. Temperature stresses or fixed beams, wherever you take it, if at all the things, deflections, if 1 deflection produces so much stress, 10 deflection will produce how much stress. Like that bending stresses also, neutral axis 0, at a distance of 200 if 100 Newton per square is the stress, at a distance of 20 from neutral axis, what is the stress? Again linear interpolation. So most of the places you have used only this much. Here also same thing. For 1 degree alpha is the strain, T degrees how much? Alpha into T. Then you can calculate strain. We also have length, change in length by original length. Then what is the delta? E into L, alpha TL. This alpha TL, delta is equal to alpha TL comes from this only. Okay. So now we'll see, these are the fundamentals we have studied in strength of materials. Taking these fundamentals, we will study how to get the relative displacement of two joints in a truss.